Every breakthrough, every scientific consensus, and every informed decision starts with two critical processes: measurement and data analysis. These are the fundamental aspects of research that allow scientists to quantify variables, test hypotheses, and draw meaningful conclusions. This lesson is from Dr. Jennifer Francia Villanueva Damo and Dr. Hernie Pina Damo. Without proper measurement techniques and robust analysis methods, research findings lack integrity, reliability, and real-world applicability. These processes are what transform a mere idea into validated scientific knowledge. Measurement is the process of assigning numerical values or categories to variables. But not all numbers are created equal. The framework identifies 4 primary scales of measurement, each dictating the level of information provided and the statistics that can be applied. First, nominal scales categorize data without order, like gender or ethnicity. Second, ordinal scales involve ranking, such as customer satisfaction levels. Third, interval scales provide equal intervals but lack a true 0 point, such as temperature in Celsius. Finally, ratio scales possess an absolute 0, allowing for meaningful comparisons of magnitude like weight or height. Understanding these scales is the first step to accurate research. How do we know if our measurements are good? By assessing 2 key factors: reliability and validity. Reliability refers to the consistency of a measurement tool. For instance, test-retest reliability ensures that repeated measurements yield similar results over time. If a scale consistently gives the same weight reading, it is reliable. Validity, however, determines whether a measurement accurately captures what it is intended to measure. A test can be reliable consistently producing the same result, but not valid if it is measuring the wrong variable entirely. Concepts like construct validity ensure the measurement truly reflects the underlying concept being studied. Once data is collected, researchers turn to data analysis. This process uses 2 main branches of statistics. Descriptive statistics summarize data using measures such as the mean, median, mode, and standard deviation. These tools help researchers quickly understand the basic features and central tendencies of their dataset. Inferential statistics allow researchers to make predictions and generalize findings to larger populations. Tests like t-tests, ANOVA, and regression analysis help determine if observed differences or relationships are statistically significant, meaning they are highly unlikely to have occurred by chance. At the heart of research is hypothesis testing. This involves setting up a null hypothesis, which assumes no relationship, and an alternative hypothesis, which proposes one. Researchers then conduct statistical tests, typically aiming for a significance level of p-value less than 0.05 to determine whether to reject the null hypothesis. However, errors can occur. A type 1 error is the incorrect rejection of the null hypothesis, a false positive. A type 2 error is the incorrect retention of the null hypothesis, a false negative. Minimizing these errors is crucial for accurate scientific advancement. Beyond the p-value, the concept of effect size is vital. This measures the strength of the relationship between variables, providing insights into the practical significance of the results. Measures like Cohen's d quantify the real-world impact of the findings. Advancements in technology have revolutionized this field. Tools like SPSS, R, and Python enable complex analyses, including machine learning and big data analytics, enhancing both the efficiency and accuracy of scientific investigation. Ultimately, measurement and data analysis serve as the foundation for scientific progress. These methods mandate rigorous ethical standards, requiring researchers to ensure data integrity, avoid fabrication, and uphold confidentiality. They also demand replication and reproducibility to strengthen scientific trust. By properly applying measurement tools, ensuring reliability and validity, and using robust statistical techniques, researchers contribute valuable, objective, and meaningful knowledge to their fields. Do you prefer using descriptive or inferential statistics in your work? What is the most common data error you encounter? Share your thoughts and questions in the comments below. Like this video, subscribe for more in-depth looks at research methodology, and hit the notification bell to become a master of scientific inquiry.